Part 3, this is for questions 21 to 30. Question 21, which statement comparing magnesium and barium or their compounds is correct? The first option, magnesium reacts with dilute hydrochloric acid more readily than barium does. So this one is actually wrong, because as you go down the group, these metals become much more reactive. Why are they much more reactive? Because when you look at the distance between the nucleus and the outermost electrons, it is too big. Okay, now that means the nuclear attraction for these outermost electrons becomes very weak. You see that? So in this one being very weak, it becomes very easy for these electrons to be lost. You see? And metals react by losing electrons. So that means going down the group, they become much more reactive. So you can't tell me that magnesium reacts much more rapidly than barium. You see that? So that one is off. Then B, 1 mole of magnesium carbonate gives off a greater amount of gas when it reacts with an excess of dilute hydrochloric acid than 1 mole of barium carbonate does. Of course, this is wrong. They all give the same amount, because you are going to have magnesium, then plus it's magnesium carbonate. Magnesium carbonate, then plus the HCl, you're going to get magnesium chloride as a salt, then plus carbon dioxide, and then plus what? Water. Even barium, it is going to give the same. Barium carbonate plus HCl, you'll get barium chloride plus carbon dioxide plus water. They are all going to give the same moles. And actually, I will put a 2 here and then here. They all give 1 mole of carbon dioxide. So this one is also wrong. Okay, then we go to C. The solubility of magnesium sulfate in water is greater than the solubility of barium sulfate in water. This one is correct. Okay, because as you go down the group, the solubility of group 2 sulfates decreases. Okay, the explanation for this, we give it in A level in chapter 19, where we talk about the lattice energy, enthalpy of hydration, and enthalpy of solubility. Okay, I mean enthalpy of solution. So this one is correct. But when we look at D, magnesium carbonate undergoes thermal decomposition less readily than barium carbonate. This one is wrong. As we go down the group, thermal decomposition of group 2 carbonates or nitrates increases. And also the explanation for this, we give it in A level again in chapter 19, where we talk about the ion polarization. Okay, so the answer is C. Then question 22, the colors of silver halides, silver chloride, silver bromide, and silver iodide differ. The solubilities of these halides in aqueous ammonia also differ. Which row is correct? Then this is silver bromide. We have to look for cream. It has to be a cream precipitate. And then a silver halide that is most soluble in ammonia. This one has to be silver chloride, because a chloride dissolves, okay, dissolves in dilute ammonia. That is the so-called aqueous ammonia, okay, in dilute ammonia solution. Then it also dissolves. It also dissolves in concentrated ammonia. Then the bromide is less soluble. Okay, I can say sparingly soluble, or sometimes they say insoluble. Okay, sparingly soluble in dilute ammonia. You see, or I mean in concentrated ammonia, this one actually dissolves. Okay, dissolves. Then when we go to iodide, this one is insoluble in dilute ammonia and also insoluble in concentrated ammonia. Okay, so which one is most soluble? It has to be what? This iodide, chloride here. So our answer is A. Question 23. The name chlorate is used for an anion consisting of chlorine and oxygen only. In a molecule of iodine monochloride, the iodine atom has oxidation number X and the chlorine atom has oxidation number Y. Now let us first look for those oxidation states. Now these two, chlorine and iodine. Chlorine is much more electronegative compared to iodine. That means it tends to pull the bonding electrons towards itself, and therefore we have the dipole moving towards the chlorine. So chlorine will have the partial negative charge, and then this one, the iodine, will have the partial positive what? Charge. So meaning this one will have +1, and then this one will have -1. Are we there? So when iodine monochloride is added to water, iodine is reduced. So here we have the +1. Okay, this one has a +1, and then the chlorine has a -1. Then when we look at the oxidation state of chlorine here, it is a -1. Okay, then for, of course, hydrogen, it's going to be a +1. For oxygen here, it will be 0, because you know the oxidation state of an element is always 0. And then this one will also be 0. Now, when you look at this this plus here for iodine, and then you look at this 0 here, there is reduction. Okay, that is reduction in the oxidation state. So meaning iodine, the iodide ions in here are reduced to the iodine. You see that? That is why they are saying iodine is what? Reduced. Okay, then of course the oxidation state of oxygen here is -2. That one of hydrogen, this is -2. Then this one for hydrogen is a +1. Now for oxygen, you can see that it is what? -2, and then here it is a 0, so it has increased in there. That means oxygen has been oxidized. Okay, there is oxidation here, so it is a redox reaction. Now they are saying which statement about the value of X or Y is correct. Now remember, the value of X is the oxidation number of iodine, this one here. So this is our X here. X is equal to +1, then Y is equal to -1. That is the oxidation number of Y. That is the oxidation number of chlorine, right? Now let's go to this one. Option A. X is the same as the oxidation number of chlorine in the chlorate ion formed when chlorine is added to cold sodium hydroxide. Let us look at that equation. You have chlorine here plus cold sodium hydroxide. This one is a disproportionation reaction. So you are going to get sodium chloride, then plus sodium chlorate 1. Okay, this one here, then plus water. To balance this one here, chlorines are 2, 1, 2. Sodiums, how many are they? We are seeing 2. So that means I will put a 2 here. Not so? So when I put a 2 here, that means oxygen is 2 and oxygen is 2. Hydrogen will be 2 and hydrogen is also 2 here. So that one is balanced there. Then let's look at the oxidation state. Of course, for chlorine here, it is 0. Here it is -1. And then for sodium, of course, it's a +1. So I'm interested in the oxidation state of chlorine in here. So if this one here is +1, then for chlorine we don't know, and then for oxygen the oxidation state is a -2, then we equate to 0 because the overall charge is a 0. Then this will be N, which is equal to 1 minus 2. That will be a -1. So when it crosses, it becomes a +1. So the oxidation state of chlorine here is a +1. Okay, and they said X is the same as the oxidation number of chlorine in the chlorate 1 ion formed when chlorine is added to cold sodium chloride. So here we are seeing a +1, and even here it's a +1. So that means our answer is what? Is A. But when you look at this other one, X is the same as the oxidation number of chlorine in the chlorate in the chlorate ion formed when chlorine is added to hot. When it is added to hot, this is what we get. You get sodium hydroxide here. So what are we getting? Sodium chloride. Then we get sodium perchlorate. Okay. Then plus water. Okay. And here we are going to get 5 here. Then there is a 3 here to make this one 6. So if that one is a 6, what are we going to have here? This one here, the sodiums, we are having 6. Then chlorine. If sodiums are 6, then I will put a 6 here. Chlorines are also 6. Oxygens are 6. These are 3. That means I will put a 3 here. Hydrogen is 6. Even here it is 6. What's the oxidation state? Here, again, I will have 1 for sodium, then plus N for chlorine, then plus, this will be 3 times -2. We have 3 oxygens, but each has oxidation state of -2, then we equate to 0. So this is 1, then plus -6, that is a -5. That means when it crosses, it becomes a plus what? 5. So I'll have a +5 here. This +5 is not the same as this +1. You see that? So that is why this one is off. Then when we go to this one, Y is the same as the oxidation state of chlorine in chlorate 1 ion. Of course, here we have seen that Y is -1. And here, the oxidation state here is +1. So this one is wrong. They are again saying Y is the same as the oxidation number of chlorine in the chlorate ion formed when chlorine is added to hot sodium hydroxide. Again, here it's a +5. This one is a -1, you see? So that is why even this one is off. Question 24. Which statement is correct? An ammonium ion is basic due to a lone pair of electrons on magnesium atom. This one is wrong, because ammonium, we see it has a tetrahedral structure, and the lone pair of electrons here has been donated to a proton. Okay, so we have dative bonding here. Okay, we have dative bonding, and this ammonium ion can actually lose this hydrogen it has shared electrons with. Okay, so it can donate that proton. In other words, it is an acid, like a conjugate acid. You see, it is a conjugate to ammonia. It's a conjugate acid to ammonia. So remember, a conjugate acid base pair, they differ in the number of protons they have. So if you have this one here and also this one here, there is 1 proton that differs in here, you see, 1 hydrogen. So this one can can donate a proton, so it is an acid, and then this one can accept, so it's a base. So it's a conjugate acid base pair. You see that? Okay, so that one is off. Then B, nitrogen monoxide reacts with peroxy acetyl nitrate to produce a component of photochemical smog. No, actually, this nitrogen monoxide reacts with unburnt, okay, unburnt hydrocarbons. Unburnt hydrocarbons. Then to produce this pan-peroxyacetyl nitrate, which is the main component of photochemical what? Smog. So this one is wrong. It doesn't react with pan. It reacts with unburnt hydrocarbons to form the pan. Do you see that? Then C, nitrogen dioxide catalyzes the oxidation of atmospheric sulfur dioxide. This is true. So I think the answer even has to be C. Why is this one true? We have nitrogen dioxide. You know, sulfur is an impurity in these what? Fossil fuels. So when it is burnt, it releases the sulfur dioxide into the air. Okay. Now, this sulfur dioxide, when it reaches in the air and then it finds the nitrogen oxides, it is going to react with it. But in particular, nitrogen dioxide reacts with sulfur dioxide to give us sulfur trioxide, then plus nitrogen monoxide. So here, So, sulfur in here has been given another oxygen, so that is oxidation. Okay, and then what happens here, because there is ready supply of oxygen in the air, the nitrogen monoxide that is produced here is going to react with oxygen, then to produce another nitrogen dioxide. You see that? Now, why is this one called the catalytic oxidation of sulfur dioxide? It is because the nitrogen dioxide, which appears to be consumed here to give us the nitrogen monoxide. Now, the nitrogen monoxide reacts with more oxygen to give us this one back. What was consumed is now regenerated. So, therefore, it is a catalyst. You see that? So, this process continues on and on. You see? So, that is why we say nitrogen dioxide catalyzes the oxidation of atmospheric what? Sulfur dioxide. Then D, they are saying nitrogen is very unreactive due to the very strong permanent dipole attractions between the nitrogen atoms. This is wrong. Nitrogen is unreactive because of two reasons. Number one, the strong triple bond. Okay. Number two, it is nonpolar. Remember, there is nitrogen here and nitrogen here. They have the same electronegativity. So if this one is pulling electrons towards itself and also this one is pulling towards itself, then the dipoles cancel out. Okay. So it doesn't have PDPD. PDPD forces, they are going to come into play if there is a difference in the electronegativities, just like we looked at iodine and chlorine. You see that? But these ones are the same, so you cannot have PD forces. You see that? So that is why this one is also off. Then question 25, the diagram shows the structure formula of a hydrocarbon Q. How many of the carbon atoms in molecule Q are sp2 hybridized? I've always explained what it means for electrons to be excited and then we get hybridization. So first of all, carbon has 4 electrons in the outermost shell. Okay, so carbon here, remember it is in position what? 6. So it is 1s2, 2s2, 2p1, 2p2. Now, let me look at the outermost shell. So we have this S and then the P. So P is slightly higher in energy compared to S. So there are 2 electrons in here and P must have a maximum of 6, but we first singly assign them to those orbitals. Okay. Then what happens is that an electron is going to be excited from here to the p orbital. So meaning we are going to have what we call degenerate. Degenerate orbitals are ones which have the same energy. Okay, so I'm going to have an electron here, then here. So because of the mixing of electrons in these two subshells here, we are going to see that they are going to have the same what? Energy. Now that is why you are seeing that I'm drawing them on the same what? Energy level compared to this one here. So we have the 2s and then the 3p. I mean the 2s and the 2p there. Now, let me just duplicate this one here and do like this. So I want to look at 2 carbons in a double bond that we are talking about here. Okay, so let's say here there is something, there is something, there is something, and there is something. So this one maybe takes up a hydrogen. Even this one maybe takes up a what? A hydrogen. Then here they can also do, we call it head-on overlap, or we can actually say that what is happening here. I want you to see here that which one can I refer to? Maybe let me refer to this one here. Okay, let me refer to those 2. So this one has 2 hydrogens. So maybe it has taken up this one. It has also taken up this one. Are we there? Then this carbon here has taken up a hydrogen here. You see that? Then after that, remember it also has this one, it is connected to, so maybe there is another carbon continuing, okay, this way, this one here, it is the one here. Then there is also in here, there is a sigma bond and then a pi bond. So the sigma bond, that is head-on overlap. So one is like this, and also the other one is like that, head-on, okay. But then we also have these parallel ones. Now this one can sideway overlap. Now after this one here, there is going to be sideway overlapping here, okay. This one is going to be the pi, this is sigma here. So we are going to look at how many orbitals in P, how many electrons in P, okay, have bonded before the sideway overlap. In other words, we mean those sigma bonds. So there is one in S here and there are two in P here. So that is why we say S, then P2. One in S, two in P. You see that? Then, don't you see one and then these two here? Then the pi will come here. So that means I have to look for that carbon which is sp2 hybridized, okay, must have 3 sigma bonds. 3 sigma bonds and 1 pi bond. Are we there? So let's check this carbon here. 1 sigma, 1 sigma. There is a sigma bond here and then a pi bond here. So, and those 3. So this 3 sigma bonds and then 1 pi bond. So this means that this one here is sp2 hybridized. Look at this carbon here. 1 sigma, 1 sigma, then there is again 1 sigma there, and then 1 pi bond. So 3 sigma bonds and 1 pi bond. That means even this one here is 1. Then we come to this one here. 1 sigma, 1 sigma, there is 1 sigma bond and then 1 pi bond. So therefore even this one is okay. But when you come to this one, those are 2 pi bonds in here, then 1 sigma, 1 sigma, this one is sp. This one is sp, this one is sp hybridized. Then this is sp3. You see? Then we go to this one here. Now this one has gotten 1 sigma bond here, 1 sigma bond here, and then 1 pi, and then 1 pi. You see that? Now this one doesn't qualify based on what we are having here. 3 pi bonds and 1 pi bond. Okay? So this one will be off. But when we come to this one here, you can see that this is 1 sigma, 1 sigma, then there is 1 sigma and then 1 pi. So this one then qualifies. You see? So how many are they? Of course, this one is sp3 because it has all the 4 sigma bonds. And then this one is also sp3. You see that? So we are having 1, 2, 3, and 4. So that means our answer is going to be B. You see? Not every double bond that you see here now, like this carbon here has gotten 2 double bonds. There is this one and this one. And then you count it as what? As sp2 hybridized. It must have 3 sigma bonds around it and then 1 pi bond to be sp2 hybridized. Question 26. Compound X is found in cell walls of some bacteria. Its structure formula is shown. Okay. Then they are saying how many stereoisomers are there with this structure formula. Now in stereoisomers, we talk about geometric isomerism where we look at cis and trans. So we look at the 2 carbon atoms that are in this double bond and they must have 2 different groups that are attached to them. Okay, then we can have the cis and what? And trans. Are we there? Now, let us look at what is here. We have this carbon here, then double bond to this one. So there are, let us look at the groups. This one, there is the CH3, then CH2, 17 of them. Then there is what else? It has hydrogen here. Then there is a hydrogen. Then there is CH2, 17 of them. Then you have the rest. So this group here is different from this. This group here is different from this. That means we are going to have geometric isomerism. So the cis and trans. Are we there? So here we have the cis and trans. Then when you come to this one here, this carbon has this group. It has the H, it has the OH, and this other group here. Okay. So this one is a chiral center. It has 4 different groups attached to it. When we also come to this one here, it is connected to this carbon here and everything this way. So that is one group. It is attached to the hydrogen there. It is attached to the methyl, and it is attached to the carboxyl group. So those are also 4 different groups. So meaning that this one is also a chiral center. Now, for a chiral center, this is what we call now optical isomerism. Okay, stereoisomerism comprises of geometrical isomerism, okay, where we have the cis and trans, and then optical isomerism, where we have the 2 non-superimposable images. Okay, so what is going to happen? These images actually are mirror images of each other. They just differ in the orientation or the arrangement of these atoms in space. Actually, that is what we call stereoisomerism. They have the same molecular formula, okay, and but they differ in the arrangement of atoms in what? In space. So suppose here, since this one is a chiral center, there are 2 of them. Suppose I label this, I label them as 1 and 2, and then I label this one, there are 2 of them, but I put a 3 and a 4. But remember here we also have cis and trans. So this is what is going to happen. So suppose here I have cis, then alongside 1 here and 3. You see, 1 and then what? 3. Then I can also have cis alongside 1 and 4. Cis here, 1 here, and 4 here. You see that? What else? We can also have cis, then here we pick 2, and then here we pick what? 3. We can also have cis, and then we pick 2, and then what? 4. Now, this one here is the same thing we are going to have when we have trans, not so? So I can take away all of this, wherever there is cis, and then I put what? Trans. So we shall have trans here, trans, then trans, and also trans. So how many do you see? There are 8. So your answer is 8. Then question 27, structural isomerism only should be considered when answering this question. How many straight chain isomers are there with molecular formula? This one here. Now we are having 1, 2, 3, 4 carbons. The 2 chlorines can be on this one. So we can have 1, 1, okay, dichlorobutane. The 2 chlorines can be on the second one here. So we have 2, 2, dichlorobutane. Okay, now when you shift the chlorines and you put them here, now the counting will change. You will begin from this side. So this will be 1, then 2. You see that? So you cannot say that this is 1, then this is 2, then this one will be 3. 3, 3, and maybe this one will be 4, 4. No. The position of the functional group has to take the least number. Are we there? So we have 1, 1, and 2, 2 there. Then what else are we going to have? We can have this chlorine now, okay, on the first one. Let me actually put these bonds here. Each carbon is supposed to have 4, right? So it can be on the first one, and then the other one can be on the second one. So we have 1 and then 2, okay? I can shift this one here, and then I put it here. It is on the 1 and the third, not so? 1 and then 3. Then I can also shift this one and I put it here. Then it can be on 1 and what? 4. So we can also have 1 and 4. 1 and 4. Then what else? We can have the chlorine here, and then another one is on this. Not so. So that will be 2 and then 3. So we can also have that 2 and then 3. Anything else? I said when you put chlorine here and then chlorine here. And again, even if you put here and then where else? On this one and then also on this one. Not so. Won't that be and then you say this is like you have removed this one from here and you say I'm putting it on this one, on the second one, and then on the fourth one. The numbering has already changed. So this is 1, 2. In fact, the 1 is here. So this will be the 1, then 2 and 3. So you are on 1, 3. So that one is not going to be 2 and then 4. You see that? So those are the only ones that we are having. So how many are they? These ones are 6. So our answer has to be A. And then question 28, they're saying that what is true of every nucleophile? A nucleophile, nucleo means the nucleus, phile means love. So what loves, what comes from the nucleus? In the nucleus, we know that we have protons and neutrons. Protons are positively what? Charged. So whatever loves what is in the nucleus must then be negatively charged because protons are positively charged. Of course, neutrons do not have the what? Do not have a charge. So those must be electrons, right? So a nucleophile is that species that must be in position to donate electrons. A lone pair of electrons, like we have seen cyanide in the reactions, okay, in mechanisms, nucleophilic substitution reactions, this one donating to a carbon, let's say with a partial positive charge. You see that? And maybe here there is a bromine, this is partial negative because this one is more electronegative compared to the carbon, so there is this polarity in here, then this one goes off like that. So there is a lone pair of electrons being donated. We have also seen OH. We can also use the ammonia. It is not necessarily supposed to be what? Negatively charged, but it donates a lone pair of what? Electrons. So that means our answer is B here. Question 29. The diagram shows a synthetic route to produce 1-methylcyclohexanol. This is the one here. Now product X is going to be what? I always said the rich get richer. So there's a carbon here with a hydrogen. The carbon here doesn't have a hydrogen. So using Markovnikov's rule, this carbon here with more hydrogens is going to first get the hydrogen from here because it is that kind of reaction that is going to produce a stable carbocation. Okay, so X here is going to be so CH2 here. Of course, the double bond will go. We shall have the CH3 here, and then the Br will be here. Okay. In fact, the mechanism is going to be like this. Let me show you. So we have the CH3 here. Okay. Now this one will get electrons from this partially positive hydrogen. I mean, it will give electrons, okay, to this partially positive hydrogen in this bond where bromine is much more electronegative compared to the hydrogen. So it tends to pull the bonding electrons towards itself. That is why it has the partial negative charge. So by doing so, of course, this one will break. And then you are going to have this one here. So we are going to have the CH3. And then there will be a plus here. So the hydrogen has been taken up by this one here. So there is a group this way, there is a group this way, and then this other one here. So they have the positive inductive effect. So they tend to push the electrons towards this. So it is much more stable, okay, compared to when you are having the CH3 here and then the pluses here. That means there are two groups here that are sending in electrons to this carbon. You see that? So this one is we can take it as the secondary carbocation, yet this one is the tertiary carbocation, you see? So that is why this one is going to be the major product. So bromine here is going to come, remember, it broke off from here, it became completely negatively charged. Then it will donate its electrons to this one here. And then this one will give you this one here. Then you have the CH3 and then the OH. Then reacting with reagent Y, we can get the OH. So this OH has actually, pardon me here, this one has to be Br, okay? Then this OH has replaced the Br. So the reagent here has to be aqueous sodium hydroxide. But if we add sodium hydroxide here in ethanol, we instead remove this, it is an elimination reaction, and we go back to this one, we get an alkene, okay? So what is reagent Y? Aqueous sodium what? Hydroxide. Where is it? It is here. So that is that. The answer is A. Question 30. X and Y are the reagents required to convert 1-bromopropane into butanoic acid. So 1-bromopropane is here, we put X, then this is cyanide. So this is a substitution reaction. Then we need to look for the identity of X here has to be potassium cyanide in ethanol. So we have to look at these two, potassium cyanide in what? In ethanol. And then when we put Y here, now this one becomes a carboxylic acid. So we just put dilute acid like HCl, then we get a carboxylic acid. So when we put dilute acid like this HCl, then the other one, because there is nitrogen in here, so the other inorganic part that is going to be, the other inorganic compound that is going to be formed is ammonium what? Chloride, okay? Yeah, sometimes it is also examined. So we are going to have HCl, so it is here and then here. So which one has gotten the 2 ticks? This one. So meaning our answer is C.